Hello. Right, today we're going to do finite state machines. Okay, so this we'll go into maybe a little bit more detail in the second year, but this is just the first year. Okay, so this is what we're going to be doing, understanding what is meant by a finite state machine. There's some uses of finite state machine and drawn simple, but enough to be able to answer the questions that you could get in an AS paper. Now this will be used later on because the finite state machine is used in is the control unit for what's called a Turing machine, which is a second year topic, but we need to understand these first. Right, so what is a finite state machine? It's a model of computation. It's a compact way to represent a set of complex rules, and we'll see an example of that in a minute. It says you'll see it in embedded devices that have limited memory, or very limited memory. Now, there's a YouTube link there to computer file video, which I'll put on Teams as well, which is worth looking at first. Vending machines is the big one that you'll see there. Okay, so characteristics. Now, what does it have? It has states. All right, so the states are modeled with a circle. We can see here, open, close, locked. So we've got a door here. Now, so what we have then is, just close that down. Now we've got a door that can be open, closed, or locked. Okay, so we have a transition that goes from one state to another, and we're labeling the transition. So we go from if you want to go to an open door to a closed door, then we go to the closed door and then open door, right? And that's essentially it. So there's nothing too tricky about that. Now, and okay, now this example here doesn't show it, but these are the different, doesn't show all of the states, and they can be. So we have a state, a start state. So we really do need to, where are we starting from? This one doesn't show a start state, for instance. And then we have an accept or an end state. Okay, now this is where we might want to end up at. All right, now obviously there's no goal on this one. We're just going to go on forever, but some of them will have a goal, like you get to 50 pence and then you can buy your packet of crisps, okay, and so forth. And then we have the transitions, which is straightforward. Now here's an example of something. Now this is, if normally we would do this in class. So if you're wearing a hat, if the customers can either ask you for an apple or a banana. If you're wearing a hat, you basically give them the opposite, okay? But if you're wearing a hat and they ask for an apple, you take off your hat, and then you're in the no hat state. If the customer asks for an apple, then you give them an apple and put on your hat. So with no hat, you get what you asked for. That the apple is the crucial one there, because that was, if you ask for an apple, is you're going to change your state from a hat to no hat. Okay, so no hat, you get what you asked for. If you're wearing a hat, you get the opposite of what you asked for, between the apple and banana. Now, to explain that, yeah, it's a bit convoluted, but you could have done this with a finite state machine much simpler. So what we're saying is that if you're wearing your hat, so we've got an input and an output there. Okay, so we're asking for a banana, we give them an apple, but we stay in the hat state. Now, if we ask for an apple in the hat state, then we give them the banana, but then we flip states to the no hat state, and then we're in the no hat state. So we ask for a banana, we give them a banana. If they ask for an apple, we give them an apple, but then flip to the other state. So the idea of that is it's a much simpler way of defining the same thing that took all of that text there. Obviously, I think you need to know what A and B were, but you get the idea. Now, another way of modeling that is called a state transition table. So basically what we have there, we have a current state, what state we're in at the moment, what inputs there might be. So the inputs are what you're asking for, and the outputs, what will we give them. And then we say the next state. So if we're in the no hat state, for instance, we ask for a banana, we give them a banana, but we stay in the no hat state. If we get the no hat, we ask for an apple, we give them an apple, but then we flip to the hat state. Okay, so it's just another way of expressing that. Okay, So which of the following strings here are valid? So this is an example now. Now we've got an accept state here. So is A on its own a valid one? Well, we start here. That's our start state. We enter an A and we end up on S1. So yes, that is a valid one. Now is A B B A A? So I go from A and then there's no way back. So the A would have been valid, but then we're entering a load of B's. But we're in our accept state, but we have to accept that. Now the next one is the 4 B's. So 1, 2, 3, 4. No, it's not valid because we're not stuck in the accept state there. And B, A, B, 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 A is a valid one. Okay, so there we go. It's fairly straightforward. Now I'm going to give you some questions on these. Those will be on Teams. Okay, thank you.